So the next bit is reactions of esters that we're missing, and specifically you'll see it's saponification and polymerization. So actually this slide here, I'm going to correct an error I made in the previous video. And so you can see, and I kind of ignored it completely in the video, the end product of the base hydrolysis is the carboxylate salt. And so you can have carboxylic acid react with any hydroxide base, and you'll get the RCO2 minus carboxylate salt. In the case they have here, sodium hydroxide makes sodium ethanoate. And it is true that as a chemist, you would probably go on to the next step if you needed to do something like with this salt. You might need the carboxylic acid that would result from the ester ultimately. But in reality, it's often not, as we'll see in the next few slides. So one way to really differentiate between acid catalyzed and base hydrolysis is that the acid catalyzed is going to make a carboxylic acid. I mean, the solution it's in is acidic, and so you should expect a carboxylic acid to be there, whereas the base hydrolysis is going to yield a carboxylate salt. If you remember anything from the first semester of this class, I'm sorry, talking and thinking and writing messed up. So carboxylate salt. This is a conjugate base of the carboxylic acid. So every acid, when they have reacted in an acid-base sense, the acid will form a conjugate base, or a base would form a conjugate acid. And so at the base hydrolysis, you should expect the opposite type of product from the acid catalyzed hydrolysis. You get the carboxylate salt, which is itself the base form, and then acid catalyzed, you get the acid form. So again, in this slide in the previous video, I made a mistake. So it says draw the line angle formulas for the products from the hydrolysis of methyl benzoate. So methyl benzoate would be, you can just use that pH for phenyl ring. So that's methyl benzoate plus KOH. That one would just yield the carboxylate salt right here, potassium, and then you would have, actually let me change some colors here so this can make more sense. Let's make this OH red, and then that would be this right here, and then you would get I'll highlight it here, you'd get that methoxide ion, but it's going to have the hydrogen on it, so you get O, and then the H from right here is that hydrogen, so you'd get methanol and this benzoate ion, or technically potassium benzoate would be the name of that whole ionic species right there. The major thing that was missing from the reactions for esters was saponification. Really, it's just base hydrolysis. It's another name for it. And that's why I said in a few seconds ago that a lot of people do leave the carboxylate salt as the carboxylate salt, because saponification is the production of soaps. A soap itself is just a series of carboxylate salts, and since they're salts, they're going to be solids at room temperature. Obviously, if you're buying Dawn dish soap, they've added water to it to dissolve the salts so that you can more easily use it, but soap bars are just these things right here mixed together. And you can see you have some metal ion and a hydroxide reacting with this, which is a fat or oil, and we'll go over those in the next chapter. So it's a good segue into the next chapter. But you get from that the triglyceride, you get glycerol as a product, and then 1, 2, and 3 carboxylate ions right there. If they're different or if they're the same, it doesn't matter. But when these things are finished reacting and you boil off the water and all the solvent and everything, you're left with soap, because those are just soaps. This slide here is showing how a soap, piece works. What it does is it forms these things called micelles. So you can see right there, that's a micelle. And so when we look at a compound, let's say we have a really long alkyl chain that was a carboxylic acid. Well, when those have reacted with a base, they're going to make the carboxylate salt. And yes, we're taking it from an ester technically, but either way, you're going to get a long alkyl chain, and this is going to be nonpolar over here. Call that a nonpolar tail. And then you're going to have this polar head to it, because you have the negative charge on that oxygen. So you have a polar head and a nonpolar tail. Well, when these soap particles get into water, the tails are hydrophobic, and so they're going to stay away from water as much as they can. And then the polar head, these are hydrophilic, and so they're going to be attracted to water. If you looked at this picture here, if I zoom in on it, you can see that in blue you have the polar heads. And then in yellow on the insides you have the nonpolar tails. Right in here. And so you can see, okay, I got water all around it, yada yada yada. The water, which mind you is polar, is going to be attracted to these polar heads. Now actually I've drawn that wrong, so let me fix this here. But you have the hydrogens of water, which are partially positive. You have the carboxylate salts of these fat molecules, essentially, that would be attracted to the hydrogen through hydrogen bonding. And you're going to have thousands of water molecules surrounding this essentially envelope of the micelle. Now what's great is that about this is the formation of this is that inside of here, in this, I'm just going to highlight it yellow, that portion is going to contain or dissolve nonpolar organic matter. That's why we use soap. These micelles at the molecular level really dissolve organic material, dirt and things like that, oils from our skin. The water itself only really can dissolve the salt. So yeah, we sweat and we stink at the end of the day, but if you just washed yourself without soap and you only washed with water, you'd still be dirty, because you'd just be getting the salt off, but none of the organic stuff that you need to slough off. The last type of reaction that was missing was the polymerization reactions. So polyesters, these are just polymers of esters. And so esters can easily polymerize. You might have heard of polyesters. They're a type of synthetic clothing or synthetic fabric. I'll say that. The example given here is the polymerization of terephthalic acid with ethylene glycol. So you can see why this works to polymerize is that the ethylene glycol has two different alcohols and the terephthalic acid has two different carboxylic acids. So in the first step of the reaction, you can see we have the carboxylic acid on the right side of the terephthalic acid. We have the other carboxylic acid right there. But we have, from the ethylene glycol, we have this portion right there. Well, when you look at it, this intermediate step, the first, this would be a monomeric unit of ultimately the plastic, has a carboxylic acid and an alcohol. And so another molecule of ethylene glycol could come in over here. Another molecule of terephthalic acid could come in over here. And so it's going to build that way and that way around it and form chains. And so as you can see right here at the bottom, you have this polymer of ethylene glycol and terephthalic acid, which we call polyethylene terephthalate, or PET. You might have heard of PETE type of plastic. And that concludes the lesson for carboxylic acids and esters.